How do you know your granola bar is really 150 calories? Yeah, sure. They might have tested it, but each bar has a different combination of walnuts, granola, and chocolate. Have you ever bitten into one and noticed it had double the amount of chocolate compared to normal? When we want to measure properties of a population, like average, it is usually hard or expensive to examine every single member of that population. Instead, a few samples are measured, but each sample can have a slightly different measurement. For example, in a randomly selected sample of 5 granola bars, the average calories might be 145, whereas another randomly chosen sample could have 175 calories. Given these constraints, how could we possibly know what the population's average is? Well, luckily, there's an extremely useful theorem and arguably one of the most important and useful ideas in all of statistics. It is called the Central Limit Theorem, and it says that for any population distribution, the distribution of its sample averages is approximately normal. And this isn't just about calories either. It's how we know the average time a medication takes to work, the average strength of the steel cable holding up your elevator, or the average amount of coffee that is safe to drink. Now, how does the central limit theory help us? Well, let's look at that granola bar example again. If we were to plot out the calories for each individual bar, we might have this weird looking distribution. It is bimodal, just meaning there are two peaks. Now, this calorie per bar distribution is definitely not normally distributed, but being normal is not needed for the central limit theorem. To see this, we can take the averages of random samples of the distribution and plot them similar to before. Let's say we grabbed a sample of 10 bars this time. We can then find their average and plot it. Then we can do the same thing with another sample of 10, and then another, and then we can repeat this thousands of times. This new graph made from thousands of sample averages is the sampling distribution, and it shows us even when the underlying distribution is not normal, the distribution of sample averages is. To put this more rigorously, as our sample size n increases, the distribution of sample means will become approximately normal, with a mean equaling the population mean and a standard error of the population standard deviation divided by the square root of the sample size. Now you might be asking, is this always the case? And it only is when our sample size is sufficiently large. Typically this value is over 30, but could be less if the distribution is already closely normally distributed. There are tons of applications for this in things like hypothesis testing and confidence intervals, and helps us make inferences about the population's mean. If this video helped, leave a like, comment, and subscribe for more videos.